Okay, we're back. Well, we have been able to handle a surprising variety of integrals already, and we have seen that there's even a way around poles on the real line. Um, However, there are also functions such as the logarithm function that don't have a pole on the real line but a branch point. And there are integrals that are interesting that contain the logarithm function or root functions. And so we also would like to know how to handle branch points and branch cut. We will see two examples here, and the first example shows that basically the same contour as what we used for poles can work rather nicely for branch cuts, but the second example, which involves roots, shows that we can't do that all the time, because for roots, of course, we can't go to the negative axis because roots of negative numbers just don't behave as nice as we would like them to behave, of course. Okay, so let's take a look at this. We want to show that the integral from 0 to infinity of ln x over x squared plus 1 dx is equal to 0. And, well, that one we actually can't tackle directly, but what we can tackle is the integral from negative infinity to infinity of the logarithm of z of the logarithm of z squared divided by z squared plus 1, where we want this to be a branch of the logarithm function. And of course, that'll be the integral from negative infinity to 0 of ln of the radius plus I pi, right? Because these numbers here are all of the form r e to the I pi, and the logarithm will be ln r, and I just stuck the absolute value in there for good measure, plus I pi. And the square of those numbers, of course, will be, well, negative number squared gives us the positive number back, so we just get r squared plus 1 in the denominator. So that looks very much like the integral that we have over here, which is the integral from 0 to infinity ln r squared plus 1. The only difference is the I pi, but that's going to make a big difference in the long run, because notice, well, we've got a square here and we don't have a square here, so something ought to give still. Well, this is the integral from 0 to negative infinity to 0. We just work out the square. ln r absolute value squared plus 2i ln r pi minus pi squared divided by r squared plus 1. The second term stays the same, and now if we pull that apart, we see we can pull out an integral from negative infinity to 0 ln r absolute value squared over r squared plus 1, which is equal, because this thing now is even, this thing is equal to this thing, and we also have left the integral from negative infinity to 0 2i ln r pi minus pi squared over r squared plus 1. If we now take this last one and put it, first one and put it together with the last one, we get the 2 integral 0 to infinity ln r squared divided by r squared plus 1. And we also get the 2i pi, we factor that out, ln r over r squared plus 1, that's this term here. And then we have the minus pi squared times the integral from negative infinity to 0, 1 over r squared plus 1. And now finally, we just resort that and change the integrals all to 0 to infinity. We've got 2 times the integral ln r squared divided by r squared plus 1. That ends up being here. We have, because we now, rather than going from minus infinity to 0, we want to go from 0 to infinity. That should still have the same signs. Give me just a minute. And we're back. Yes, those were supposed to keep their signs because these that's an even function, which means the integral from negative infinity to 0 is the same as the integral from 0 to infinity, and similarly this is an even function, so that integral also is the same. What we see, however, here is that the integral that we are after, this integral up here, is actually part of the imaginary part of this integral here. So we're just going to start messing with this integral, and anything that affects the real part we can actually leave alone and just concentrate on the imaginary part. So how do we do that? Well, we're going to do the same thing as before. We now have an integral from negative infinity to infinity. So we start at a large negative number, squeeze our way around the branch point at 0, then go back to a positive number, and then close it up with a semicircle. So again, the smaller circle will go from negative r to r. The larger circle will go from, well, r to negative r if we're following the orientation. We'll call the inside S1, we call the outside S2. We're not going to worry too much about orientations this time. And so now then, of course, in order to get the integral over this closed contour, we need to figure out the residues in the upper half plane. Well, there is a simple pole at I, and so we need the residue at z equals I of ln z over z squared. Ln z squared over z squared plus 1. And, well, that is done same way as before. Take the derivative of the denominator. No, actually, we are just factoring the denominator. We have this part which gives us the pole, and we've got that this is an analytic function, which means the residue now is the value of this function at I. So that'll be ln I quantity squared divided by I plus I. Well, the denominator is 2I. The logarithm of I, remember, I is e to the I pi over 4, so the logarithm will be I pi over 2, if I'm correct. Yes, all right. And, well, that gives us I squared pi squared over 4 divided by 2I. And the I squared is a negative 1. Pi squared over 4 divided by 2 is pi squared over 8. And the I stays in the denominator. And minus 1 over I is I. And so that ends up being pi squared over 8 times I. So that residue actually deals with the imaginary part. But that means, on the other hand, that residue is imaginary, but that means that 2 pi I times this residue is equal to negative pi cubed over 4, and that does not contribute to the imaginary part. So even though the integral is ultimately non-zero, the imaginary part, and that's all that we're interested in for this computation, the imaginary part of that integral is equal to 0. Okay, so now we need to figure out what happens along those circles. Well, let's first look at the small circle S1. Take the absolute value, and we do the usual thing, triangular inequality. We pull the absolute value inside and integrate against the arc length. Well, we know that because on this circle, the absolute value of z is r. That means that this will be ln r plus some number between 0 and pi in the imaginary part, and so that's definitely smaller than ln r absolute value plus pi. And in the denominator, we must have that the denominator is greater than 1 minus r squared. Yeah, the smallest number will be in the denominator when z is ir, because then we subtract r squared from 1. And so that means if z squared plus 1 absolute value is greater than 1 minus r squared, then its reciprocal is smaller than 1 minus r squared. So that's how that one works out. Well, now we realize that this is less than or is equal to pi r, because we're only going halfway around the circle. Right? It's bounded by, well, the arc length is pi r times the value of the integrand, which is now a constant. And we realize as r goes to 0, well, we have that the denominator would go to 1. And the numerator goes to infinity like ln r squared, but r times ln r squared actually goes to 0. That's something you can verify with L'Hopital's rule. So that goes to 0 as r goes to 0. Similarly, as we are looking at the larger circle, we do the same estimate. We pull the absolute value inside, and this time, of course, again, the logarithm is less than ln r plus pi. And this time around, z squared plus 1, well, z has magnitude r, and the closest that gets, or the smallest that gets, is r squared minus 1, which means that the reciprocal is larger than 1 over r squared minus 1. That's something you can also draw geometrically if you wish. Again, we get pi r times the value of the integrand. Well, that gives us still something on the order of r in the denominator, and ln r, even ln r quantity squared divided by something on the order of r goes to 0 as r goes to infinity. That's another L'Hopital's rule there. And well, now we have that this integral is 1 over 2 pi times the imaginary part of the integral from negative infinity to infinity ln of z quantity squared plus 1 dz, which is 1 over 2 pi times the limit as lowercase r goes to 0 and uppercase r goes to infinity of the integrals from negative r to r plus the integral from lowercase r to capital R. And what did I do here? There's not much happening. Oh yeah, sure, you can move the limit outside the imaginary part. And then, of course, this is minus, because we knew that the imaginary part of the contour integral was equal to 0. This is minus the limit of the imaginary parts of the integrals that complete the contour. But remember, these integrals go to 0, which means their imaginary parts go to 0, and that means that that limit is equal to 0. Okay, well, it always seemed so far as if we just flip around the singularity or the branch point. It turns out when we're dealing with root functions, and that's what we're doing in this example where we want to talk about 0 strictly smaller c strictly smaller than 1, and we want to show that the integral from 0 to infinity x to the minus c over 1 plus x dx is sine pi over sine pi c. If we want to show that, we actually have to do the following. We'd like to take our integral and complete it with an integral on the negative axis, but that would be problematic because even though, of course, with complex numbers we can take roots of negative numbers, we don't have nice symmetry properties anymore. I mean, we still had the symmetry properties for the logarithm, which helped us a great deal, but for these guys, okay, let me be perfectly honest, I haven't tried it with the same contour as before, and any book I've looked at had the approach that I'm presenting here, but I would think that means that there is something that doesn't quite want to work out. So rather than completing the contour with something over here, what we do is we go all the way around, then back, then all the way around the branch point in the positive direction to use this contour. The important thing to always realize with functions that have a branch cut is that you somehow must have your contour avoid the branch cut. And if I just want to use a branch cut that goes along the real axis or slightly below the real axis here, then that is something that I most certainly can do, and all the computations will still work out fine. Now, the upper circle will be called C lowercase capital R, and the smaller circle will be called K subscript lowercase r. And the width of this slit here, the picture was getting a bit too busy. Basically, I want from the axis to this guy here, I want that to have height delta, and from the axis to this guy, I want that to be height negative delta, if you will. And if I then integrate over this whole contour, which depends on gamma, which is why I wanted to call it gamma delta, if I integrate z to the negative c1 plus z over that, well, that's 2 pi I times the residue at z equals negative 1 of this function, because that's, well, that's the only singularity, and that's a simple pole, which means this is 2 pi I e to the negative I pi c, and that is because if I plug in negative 1 here, this is just 1 over 1 plus z times z to the negative c, and the residue will be the value of z to negative c at negative 1. Okay, so that would be negative 1 to the negative c, and remember negative 1 is e to the I pi, which means we get e to the negative I pi c here for that value. Okay, so as you can see, these computations get lengthy enough that certain other sub-computations that we previously had practiced by themselves, we just weave in as necessary. Okay, and I think that's also one of the reasons why you don't want to go to the negative axis here. It's not so much the root function, it's the fact that you've got another singularity here and you'd have to deal with it too. Okay, now what? Well, the limit as delta goes to 0 from above. Say we integrate, remember that slit had width 2 delta, so it had a horizontal line at I delta and it had a horizontal line at minus I delta. If we integrate from r plus I delta, lowercase r plus I delta to uppercase r plus I delta, z to the negative c, 1 plus z, and let delta go to 0, well, then that's the integral from r, lowercase r to capital R of x to the negative c, 1 plus x. That's not a problem. If we let the same delta go to 0 for the integral over the line below the slit, well, then we get that this is the limit as delta goes to 0 of the negative of the integral from lowercase r minus I delta to uppercase r minus I delta. So I just change the order in which I go through that. And then that is, well, let's see. Now we're working with the principal branch or with a branch of the root function. And if we go towards the x-axis from the fourth quadrant, that means that our numbers are of the form x times e to the I 2 pi minus a little bit. And so that means that z is ultimately x e to the 2 pi I. Well, I factor out the e to the 2 pi I to the negative c, which is this part here, and I keep the x to the minus c 1 plus x, which is of course the integral that we're interested in. The integral over the contour is bounded by what we get when we pull the absolute values inside, which is this time actually length of the contour, bounded by the length of the contour 2 pi r, times, and on the contour here everything has absolute value r, so this becomes r to the minus c, and 1 plus z again is, at the worst, the smallest it could get is r minus 1, so this thing is bounded by 1 over, so the 1 over 1 plus c is bounded by 1 over r minus 1. And that still goes to 0 because r over r minus 1, well, that goes to 1, but r to the minus c goes to 0, so we're good with that. As r goes to infinity, and the small contour, we do the same estimate, and this time we get that, well, okay, the length of the contour is bounded by 2 pi r. If everything has absolute value r, then z to the minus c has absolute value r to the minus c, but this time we're inside the circle, so this time the smallest 1 plus z can get is 1 minus r, and that means 1 over 1 plus z is bounded by 1 over 1 minus r. And this time around, well, as r goes to 0, this guy goes to 1, but r to the minus c, remember c is smaller than 1, so we get r to the 1 minus c, which still goes to 0 also as lowercase r goes to 0. Well, that gives us the following. Basically, this residue that we had, the 2 pi I e to the negative I pi c, that's the limit as delta goes to 0 of the integral over this contour gamma delta z to the negative c over 1 plus z dz, and that's the limit as delta goes to 0 of the integral over the horizontal piece going out, plus the circle of radius, well, not quite r, really, because we have to adjust the points, right? But that was a technicality that I chose to omit in this presentation. Plus the integral of the contour where we're coming back, plus the integral over that small circle kr, and that'll be the integral, that goes to the integral from lowercase r to uppercase r x to the negative c over 1 plus x dx, plus the integral over the whole circle. Okay, yeah, the delta just means that we cut out a little delta there. The little piece that kept the circle from being complete. Minus e to the negative 2 pi I c integral from r to uppercase r x to the negative c 1 plus x dx, that was also shown on the previous panel, plus the integral over the full circle z to the negative c, 1 plus z dz over the full circle kr. And then we know that, well, those were the limits, and we can now let r go to 0 and capital R go to infinity. And we keep, of course, all those integrals that we had on the previous panel. But now the first integral becomes the integral that we want. The next integral goes to 0 as we had shown. This integral becomes e to the negative 2 pi I c times the integral we want. And the last one goes to 0 again, just like we've shown 2 panels ago. And that's 1 minus e to the negative 2 pi I c times the integral that we're interested in. Solve for that integral, and we get that the integral we're interested in is 2 pi I e to the negative I pi c from here, divided by the denominator, which comes, of course, from here. Well, we pull the pi out, we keep the 2i, and if we multiply numerator and denominator by e to the I pi c, then this guy here vanishes. The 1 becomes e to the I pi c, and the e to the negative 2 pi I c becomes e to the negative pi I c. And if we look at that real hard, we realize that that really is sine pi c in the denominator, because this is just a reciprocal of sine pi c. And, well, that's what we were supposed to prove here. Okay, one more example, one more approach, and that is, how do we handle sines and cosines on finite intervals? And there's a very nice substitution, which is that if you have anything that depends on sine theta and cosine theta, and you want to integrate it from 0 to 2 pi, that's the same as when you integrate over the unit circle the function f of z minus z inverse over 2i, z plus z inverse over 2 dz divided by iz. Why is that? Well, C is the unit circle, and on the unit circle, z minus z inverse divided by 2i, that's sine theta, and z plus z inverse divided by 2, that's cosine theta, because on the unit circle, z is e to the I theta, right? So the expressions for sine and cosine follow from z equals e to the I theta and the Euler identities. And for the substitution, we want to realize that dz d theta, when z is e to the I theta, is just I e to the I theta, which is iz on the unit circle. So that means dz over iz is d theta. And so that is how that substitution works. And as an example, we want to show a rather horrible integral. We want a to be between negative 1 and 1. And we want to prove that the integral from 0 to pi cosine 2 theta 1 minus 2a cosine theta plus a squared d theta is a squared pi divided by 1 minus a squared. Well, first thing we realize is this is not from 0 to 2 pi, and for that substitution we really need the full unit circle. Well, let's take a look at the integral from negative pi to 0 cosine 2 theta over this rather horrible denominator. Well, that's if we're doing a substitution theta equals negative mu, or mu equals negative theta. Either way, we get d mu d theta being negative 1, and so theta is negative 1 d mu. Theta is minus mu, that works out, and when theta is negative pi, mu is pi. When theta is 0, mu is 0, so that's just a straight substitution as we see it in regular calculus. And this negative 1 flips the integral, so this is actually the integral from 0 to pi cosine mu, cosine 2 mu. There, integral from 0 to pi cosine 2 mu divided by 1 minus 2a cosine mu plus a squared d mu, where of course the negative signs here go away because the cosine is an even function. And, well, that means that the integral from 0 to pi of this integrand is equal to 1/2 times the integral from negative pi to pi of this integrand. And that's 1/2 times the integral from 0 to 2 pi of the integrand, where I now also want to go back to just cosine and sine theta. Well, cosine 2 theta is cosine squared theta minus sine squared theta. That's the trig identity, and the denominator stayed the same. And now we can do our substitution. So this is 1/2 times the integral over the unit circle, z plus z inverse divided by 2 quantity squared, minus z inverse over 2i quantity squared, 1 minus 2a z plus z inverse divided by 2 plus a squared dz over iz, and I just copy that over to the next slide here. And now we just do algebra. We just multiply things out. So what is this? We have a division by 2 squared, which would give us a division by 4. We've got a division by 2i squared, which gives us a division by 4, negative 4. Minus minus is plus, and so we have a division by 4 and a plus up top here. Well, the division by 4 is 1/4. The minus becomes a plus, and then we just kept this guy to be this with a square, and this guy is this guy with a square. In the denominator, I just canceled the 2's. Not much happening there. Now let's multiply out the squares. So the 1/4 is pulled out. Not a problem with that. If you multiply out the squares, the mixed terms go away, right? Because you get 2z inverse minus 2z inverse. And other than that, you have z squared and z squared, which gives us a 2z squared. And you get z to the negative 2 plus z to the negative 2, which is 2z to the negative 2. And in the denominator, I took the z from back here and just multiplied that in. So we get z minus az squared from here, minus a, because z times z to the negative 1 is 1, of course, plus a squared z. We still have the I here. And basically in these computation, a good first step always is try to eliminate all the z inverses, and that's of course what we have achieved here. Now let's see. The 2's come out, so the 1/4 becomes a 1/2. 1 over I is negative I, so I pulled that out too. I get negative I over 2. And then we multiply numerator and denominator with z squared, which gives us 1 over z squared here. And in the numerator, of course, I get z to the 4th plus 1, and that takes care of the last negative exponent in z. In the denominator, nothing happened except that I've sorted some terms. So we've got the negative az squared right here. We've got 1 plus a squared times z here, and we've got the minus a here. So that's just cleaning things up. And of course, now this is something that we want to solve with the residue theorem, and we know that there is a singularity at the origin, but we also have a singularity wherever this horrible denominator is equal to 0. And so, let's see, yeah, that's exactly what we're going to do. Negative I over 2 is copied, 2 pi I times the sum from the residues here, zj's, pole or singularities that are in the unit circle, and we want the residue at z equals zj of this horrible thing here. And that would be, well, you'd cancel the 2, I squared is negative 1, cancels with the I, cancels with the negative 1, so we just keep a pi out front, everything else stays the same. And so now we need to find the residues at those singularities, remembering that we also have a singularity at 0. So we take this horrible denominator, set it equal to 0, and inflict the quadratic formula on it. Well, negative, the linear term, plus minus square root of square of the linear term, minus 4 times the term in front of the z squared times the constant term, that's minus 4 times negative a, so that's minus 4a squared, divided by 2 times the term in front of the z squared, which is 2 times negative a. Okay, so push the negative sign into the numerator. That cancels this negative sign, so we get 1 plus a squared. Technically speaking, the plus minus, even though it doesn't matter here, turns into a minus plus. We have a 2a in the denominator, and we multiply out the stuff inside the square root, so we get 1 plus 2a squared plus a to the 4th minus 4a squared, and then of course those two can be combined, so everything stays the same except that the plus 2a squared minus 4a squared becomes a minus 2a squared here, and that's a perfect square. So this is 1 plus a squared minus plus square root of 1 minus a squared quantity squared divided by 2a. Take the root of that. Well, that gives us 1 plus a squared minus plus 1 minus a squared as a quantity divided by 2a. And that would give us on one hand a, right? Because if we subtract, we get 1 minus 1, which goes away. A squared minus negative a squared gives us 2a squared divided by 2a, that's a. And we also get 1 over a, because when we add, we get 2 over 2a, which is 1 over a, because a squared minus a squared, of course, goes away in that case. And because a is between -1 and 1, the solution 1 over a is outside the unit circle. And that means we only have to worry about the pole at a. And the pole at a is simple, because after all, a quadratic can only have 2 zeros. If it has 2 distinct zeros, then they're both simple zeros. And so that means that the residue at z equals a of this horrible looking integrand, let's see how we're proceeding here. That's the residue. Yeah, we're just going to use this theorem that says take the numerator divided by the derivative of the denominator. So I multiply the z squared in to get negative a z to the fourth, 1 plus a squared z cubed, and minus a z squared. And that gives us the numerator divided by the derivative of the denominator, which is negative 4az cubed plus 3 times 1 plus a squared z squared minus 2az at z equals a. And if we plug in a, we get a to the fourth plus 1 minus 4a to the fourth plus 3a squared. I already multiplied that out. 3 times 1 times a squared plus 3 times a squared, that's 3a to the fourth minus 2a squared. And then, of course, we do the subtraction here. We get a to the fourth plus 1. Negative 4a to the fourth plus 3a to the fourth is negative a to the fourth. 3a squared minus 2a squared is a squared. And so that's the residue at a. Well, the pole at 0 is not simple. So here we, in order to find the residue, we actually have to use that other theorem that we had. If the singularity is factored out, if it's 1 over z squared times something that is analytic at 0, then the residue will be the derivative of this thing that is analytic at 0 divided by 1 factorial for a pole of order 2, which is what this is. And so here we have to use the quotient rule, which becomes rather horrible. Derivative of the numerator is 4z cubed times the denominator minus derivative of the denominator, which would be negative 2az plus 1 plus a squared, quantity closes, times the numerator divided by the denominator squared. And of course now you can do a lot of algebra that could make your life really hard, or you could realize that we only are interested in this thing at z equals 0. Well, at z equals 0, this whole thing goes away, which is great. So we're going to plug in z equals 0 right away. And that means this stuff goes away, 2az goes away, we keep a negative 1 plus a squared times 1, so that's just all that survives in the numerator. And in the denominator, we end up with a negative a quantity squared, which is a squared. So that's perfectly fine. And so now adding the residues at 0 and at a gives us, well, the residue at 0 was the negative 1 plus a squared divided by a squared. The residue at a was a to the fourth plus 1 over negative a to the fourth plus a squared. So now we expand with negative a squared plus 1 in the first one to find a common denominator. This is now just a lot of rather horrible algebra. So we expand. And as we do that, well, we get the same denominator. The a to the fourth plus 1 comes from right here. And realize that this is 1 plus a squared times 1 minus a squared. So by binomial formula, we get that this is, keeping the minus sign, 1 minus a to the fourth. And that's, of course, now minus a to the fourth plus a to the fourth is 2a to the fourth. Minus 1 plus 1 goes away. And in the denominator, I can factor out an a squared, and I've got a 1 minus a squared there. And that is 2a squared over 1 minus a squared, canceling the a squareds. And that means that the integral is 1/2 times this integral after we've done the substitution. And that is 1/2 times pi times 2a squared over 1 minus a squared. And that is because we are already done with those residues, I think. And that's it. Give me just a second here. Yeah, that was indeed correct. After you've dealt with the residue theorem long enough, you automatically key in on a 2 pi or a 2 pi I. But in our computation, our initial computation with this integral, we saw that this was just going to be pi times the sum of those residues. And then, well, the last step here is a simple simplification. The 2's cancel, and you put the pi in the numerator there. Okay, that was the calculus of residues. This is one of the high points of the course, if you will, because there's a lot of good computation as well as a lot of good estimation going on, together with really neat visualizations in the complex plane. So yes, those problems, just as the examples, will take quite a while, but do take some time to enjoy them. These computations, once you can do them reliably, um, are something that will just make you stronger, because there are very few computations after that that will ever bother you again. Okay, with that, I'll leave you to the homework. I'll see you.